So I will start the lecture again. So in the first part of the lecture, I showed how you can count 0 or 1 photon. And of course, since 0 and 1 is given by 1 bit of information, you need only 1 atom to do that. When the atom gets, if you have a field which is 0 or 1 or a superposition of 0 and 1, and you send 1 atom, by detecting the atom, you collapse the photon number either to 0 or to 1. Now, of course, what we want to extend this, what we want to do is to extend this to measuring larger photon numbers. And if you want to do that, you need more than 1 atom. If you want to do it in an optimal way, you need at least the number of atoms which are required to read the photon number in basis 2. For example, if you want to measure between 0 and 7 atoms, you need at least 3 bits, because 2 to the 3 is equal to 8, so that gives you the information from 0 to 7. So that's what we want to do, but of course, what we do is not optimal, so we will need more than this number of atoms to get the information about the photon number. So I raise a question here on the next slide. In fact, we will use information which is carried by off-resonant atoms to measure the light shifts which are induced by the photons. The atoms are destroyed when they are detected, but the photons are not. It's a non-resonant interaction. And what I want to stress is that this is something which is quite symmetrical from ion trap physics. In ion trap physics, you use photons to decide in which state the atoms are. So you kill photons, you destroy photons to get information about atoms. Here we do the opposite. We destroy atoms to get information about photons. So it's exactly the same kind of things. And in fact, it's striking that the ion trap physicists and the cavity QED physicists are doing the same thing seen from 2 opposite viewpoints. We will see also that we can see quantum jumps exactly in a similar way as we see quantum jumps on atoms. Here, the quantum jumps will appear as a very fast disruption of a sequence of atoms leaving the cavity. So let's analyze this in more details. Again, we work with the Ramsey interferometer, and I will present here the Ramsey fringe signals that you get for different photon numbers. If you have 0 photon in the cavity, you get Ramsey fringes. If you have 1 photon in the cavity, you get fringes which are shifted. And of course, now I use a shift which is more generous than a pi phase shift per photon. We see that we need smaller phase shift per photon. This is what you get with 1 photon. If you have 2 photons, you get this, and so on. And so you see that you have fringes which are shifted by a quantity which is proportional to the photon number. So let's fix your interferometer at a given phase. You see that if you set the interferometer here, you get a signal which varies here if you have 0 photon, here if you have 1 photon, here if you have 2 photons. But what is this signal? This signal is an average. It's something that you obtain because it's a probability. So you have to detect a lot of atoms to find whether it converges to one value or the other. So the big difficulty of the experiment is to be able to get enough information in a time short compared to the damping time of the field. And the larger the photon number, the faster the field will damp, the photon number will damp. So it's a race between acquiring information and damping. And this explains why you cannot do that for large photon numbers. We are restricted practically to a photon number between 0 and 7, the kind of order of magnitude that I discussed before. So what you have to do is quite clear. You have to pin down the photon number by getting enough statistics accumulated in a time short compared to the damping time of the cavity.
Here, this seems to violate what we say, right? Because
excuse me?
This seems to violate what we say, because here with 1 atom, you are detecting up to 3 photons.
No, it's not with one atom. In order to get, if I want to know whether I am at this point, that point, or that point, I have to detect a lot of atoms because of the signal to noise ratio. So you need a lot of atoms. But I will show you how it works. In fact, the atoms are going one by one. So you get an information progressively because once the atom is detected, you send immediately the information to a computer, and the computer updates its information depending upon the result of the measurement. And I will describe you how it works now. So how did we do that? First of all, you have to prepare in the cavity a field. And the way we prepare it is to use a classical horn here, which sends a pulse of microwave. And I told you last week that a pulse of microwave is a coherent field, which has a Poisson distribution of the photon number. So I choose a very small pulse, which has a photon number varying between 0, 1, 2, 3, 4, 5, 6, 7, something like that. And it has a maximum around 3 or 4 photons. But I don't know, and I don't even have to know that it's a coherent field. I just have to know that the photon number is bounded by some value because I have to decide what are the settings that I have to use. So I start with such a coherent field, and I remind you that the fluctuation in the photon number are related to the fluctuation in the phase. So a coherent field has a relatively well-defined phase because it has a dispersion of the photon number. And this is something which we discussed at length. And I will show you now that by detecting atoms one by one, I get progressively the collapse of the field into a Fock state. Fock means photon number state. And this illustrates the 3 postulates of a quantum measurement that I described in the first lectures: the state collapse, the statistics of the results. If you do the experiment many, many times, you should reconstruct the initial Poisson distribution, and also the fact that the experiment is repeatable. Once you have obtained an eigenstate, the system stays in the same eigenstate as long as you don't have relaxation. So how does it work? Again, I show you here the setup. It's a Ramsey interferometer. Atom in level E undergoes a shift in one direction, in G in the opposite direction, a pivot pulse here, a pivot pulse here. Each atom is kind of clock. And I want to measure the dephasing of this clock when it crosses the cavity. At time t equals 0, I don't know anything about the field, so I will not even assume that the field is in a coherent state. I just say I have no information except for the fact that I have a maximum seven photons. So I assume a flat initial distribution, not know anything about the field. And since I want to distinguish between 0 and 7, it is clever to choose a phase shift per photon equal to pi over 4. And I will show you why. If you have a phase shift per photon equal to pi over 4, it means that the spin, the dipole will get out in this state if you have 0 photon, in this state if you have 1 photon, in this state if you have 2 photon, here 3 photon, here 4 photon. So in fact, you have a different direction for each photon number. And moreover, when you detect in a given direction, of course, you don't know whether you will find plus or minus. And this is completely random. What you have to do is to choose a direction. And how do you choose a direction? You choose it by just choosing the phase difference between these two Ramsey zones. And you choose it freely by just setting the right frequency for the Ramsey signal. As I told you, the free parameters that you have an interferometer is the common frequency of the two feeds, which determines the phase shift for the atom from one zone to the other. So you choose a given phase, which, what does this pulse do? This pulse takes a spin in one of this direction and brings it back along Z, which means that after this pulse, when you measure the atom and find it in E or in G, it is as if you find the spin up or down. So the second pulse has a property of rotating one direction in the transverse plane back into the direction which is the direction along which you measure, because the only thing you can measure is E or G. So you choose, by choosing the phase of the second pulse, you decide whether you measure it here, 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 in this direction. You choose the direction along which you measure. So what happens, and I show you here what happens. Suppose that you decide to choose this direction corresponding to either 2 or 6. If you find the spin in the plus direction that is determined level E, it means that you are measuring it, you are finding the spin plus in this direction. And if you find in the minus direction, you find it here, okay? So what does it mean? What I claim is that if you find the value j equals 0, which means in this direction, it means that you cannot have 6 photons. And the reasoning is as follows. If you had 6 photons, the spin will be pointing in the opposite direction. And the probability that you would get your result would be 0. So you cannot get this result. You cannot get the spin pointing along this direction if you had 6 photons. This is a kind of classical argument. And in statistics, it's called Bayes' law. Bayes' law, it's a statistical argument which tells you, once you get an information, what was the probability of the cause of this result. And here, the cause of the result is the photon distribution. If you get the result, the spin pointing in this direction, it means that you could not have 6 photons, because if you had 6 photons, the probability to get this result would be 0. And you can go further, and I will show you in a moment what happens, that you see that the probability to have 5 and 7 photons is rather small, because if you have 5 and 7 photons, you would be almost in the opposite direction. And the likeliest is, of course, that you had 2 photons. So in fact, what you see is that you modulate the information that you have acquired, modulates your photon number distribution by a cosine law proportional to n, which represents the fringe pattern. If, on the other hand, you had found, by making the same measurement, if you have found the opposite value of the spin, the same argument tells you that now it's 2 photons which is forbidden and 6 photons which is most likely. And you see that it means that a measurement in quantum physics is an acquisition of information through a measuring device. And when you acquire some information, it changes the a priori probability law that you had before. And it changes it depending upon the result. And since the result of the experiment is random, it means that this acquisition of information is also random. You don't know what you will find, and you don't know what will be the final result. So you see that. And what I want to say now is that this is a direct illustration of the projection postulate. Here, I just try to make you understand qualitatively that you have multiplied your initial distribution by this function. But in fact, I can show it exactly by using the fundamental laws of a quantum measurement. What are we doing here? We start with a quantum state, which is the atom in the field in a superposition of n state and the atom in state E. What does the first Rabi pulse? It transforms E into E plus G. So you get now a state which is Cn En plus Gn. It's not an untangled state, and it's a product of a field state by E plus G. Okay, so you have this state, and now what do you measure? What happens when the atom crosses the cavity? This part of the wave function is affected by the phase shift, EIN phi naught, and now the system is entangled. Because you see that the state of the field is, the number of photons is imprinted on the phase of the atom, so now we have an entangled state. And the entanglement has occurred via a non-resonant process. So now you are at the exit of the cavity, and you measure. And as I told you, what you measure, in fact, is the projection on a transverse state in which you choose freely this phase, which is the phase of your detection, the phase that you apply in the second Ramsey zone. So what you have to do to get the probability is to look at the probability that this state projects on that one. So you have to take the scalar product of this state by that state. And when you do that, you find exactly this quantity. And then you have to take the square of this quantity, and you will find Cn squared, which is the probability to have n photon, multiplied by a moduli function, which is a cosine. This quantity squared, the modulus is a cosine function, you get this quantity. And so you see that you have, in fact, what you have to done is that you have multiplied Cn squared, which is the probability of the initial state that you don't know, by this quantity, which is just an oscillating function. And the randomness comes from the fact that you will detect the plus or minus sign randomly from one atom to the next. So, and this is just what I have applied here is exactly the projection postulate of quantum physics. But what I wanted to stress is that you do not need to do it. On the previous slide, I used Bayes' law, in fact, which is a classical law. And you get the same result from the classical argument, statistical argument, or the quantum one. So now you understand what happens. We send a sequence of atoms, and to pin down the photon number, you send the atoms one by one, and you detect each atom. And for each atom, you choose one of these angles, and you can choose them either periodically or randomly. And I call this direction A, B, C, D. And for each atom, A, B, C, or D, you will find 0 or 1 for the result of your spin position. And what you see is that the probability to have n photon will be the product of all these functions. Each time you make a measurement, you multiply by something which will kill some photon numbers. The values for which this quantity is 0 or near to 0 will decrease the probability of a given photon number. And so you see that your signal now is a random sequence of 0 and 1 correlated to the chosen direction of the measuring polarization. So in fact, it looks like a secret code. It's a sequence of 0 and 1 that you can read, which makes sense only if you know what is the sequence of ABCD that you have below. But when you know that, you know this function, and the computer update for each atom. And what the computer shows and what simulation shows is that very quickly, or not very quickly, but after a few tens of atoms, you converge to a given n. Once you are in a given n, you cannot suppress everything because then the wave function will have collapsed. But the result of this random decimation makes you end up with a given n. And if you do it again, you will find a different n. And a third one, you will find another n. And if you make a huge number of such complete measurements, you will reconstruct the Poisson distribution of the initial state. So it's what I show on the next slide. And so we were very excited when we got this result, because I think it's the first time that you observe a progressive collapse, which is a really progressive acquisition of information. Usually you get everything immediately. Here you can really see atom per atom, that is bit per bit, how the system decides to end up in one Fock state or another one. So you see here one event. This is the trajectory of the field. We start with, you see here the photon number from 0 to 7. And on this abscissa here, we have the number of atoms. So as you increase the number of atoms, you see that your probability evolves. Here, the system has hesitated a lot between this number and this number. You see that the dark blue number has increased and then collapsed. This number has increased and collapsed. And finally, the system has settled into this number. So it takes some time. There is an hesitation. And after a time, the system collapses. Here, the system has collapsed with 5 photons. If we do it another time, you see here a sequence which has collapsed into 7 photons. And then we did it again and again. And if you have thousands of these trajectories, you reconstruct the Poisson distribution of the initial state. So you see that the evolution of the inferred photon number along independent sequences, which measure an initial coherent state. And this illustrates the fact that quantum physics is random, because you never know on which trajectory you will end, what will be the photon number in the end. And this was performed in 2007. You see here what happens if you go on measuring. You see here a sequence which end up into the 5 photons. And you see, so after a while, after about 20 or 30 atoms, the system has decided that you have 5 photons, and you see that it stays for a long time, a relatively long time. This is a postulate about the fact that you can repeat the quantum measurement. And then at some point, the photon is lost. And when this photon disappears, it is the number 4 which appears, of course, because it disappears by a cascade. If you have initially 5 photons, when one photon disappears, you jump on 4, then you jump on 3, 2, 1, and 0. And you see here how along a long trajectory, the photon number evolves step by step towards vacuum. And each time the photon number changes, this is a quantum jump. It's sudden. So you see that if you look at a quantum system, if you observe it, the evolution is quite different from the classical one. You see it evolves by jumps, exactly like the atom, the quantum jumps in atoms. The wave function always evolves continuously, but if you measure, you perturb the system with a measuring device, and then you force the system to evolve by quantum jumps. And of course, if you average over a large number of such trajectories, you find an exponential smooth decay of the field intensity, as I will show you in just a moment. Another way to look at, so you see what happens. At the first stage, you have the field collapse, the repeated measurement, and then quantum jumps back down to vacuum. And I emphasize the fact that this is a single realization of the experiment. It's a long sequence of atoms, each atom providing an information about the way the field has evolved.
The initial state with 5 photons is due to a thermal state?
No, it's a coherent state. We start with it's exactly the same experiment as before. We start with a coherent state, and then a 5 photon is selected in this case. And we follow how this 5 photon state evolves in the following. Again, this is an example in which you start the system collapse. So you have the collapse, you collapse into a 5 photon state. It goes to 4, to 3, to 2, to 1, and to 0. And you see the quantum jumps of the field. And how do you compute this trajectory? You just, at each stage, the computer tells you what is the probability of the distribution, which is this product of cosine function, and the average photon number is just sum over n times this. So you get this kind of staircase trajectory. And you see, again, the repeated measurement, the jumps, and these are stochastic trajectories. Here you see other examples. This is a 7 photon state, 7, 6, 5, you don't see 4, 3, 2, 1, and 0. And you see it's completely random. For example, the 1 photon state, this process has lasted very long. Here you see 4 trajectories corresponding to initially 4 photons. And you see this one is interesting because you see you go to 1 and then back to 2 and then to 1. This is because sometimes you have a thermal photon coming in. And you see that you have all this which can be clearly understood. And by analyzing these trajectories, you can measure the average lifetime of each Fock state. And what you find is that the Fock state n decays in a time 1 over n. If you have n photons, the n photon state decays n times faster than the average energy. And this is quite clear also. It's a kind of classical argument. If you have n fishes in a pond, the time it will take to fish the first fish will be shorter and shorter if the number of fish increases. You will have a higher probability to lose the first one. And it's exactly what happens with the photons here. And here it's also interesting what I show here. From the data, what you can get is the probability pi n to have n photon in the field as a function of time. So you start by analyzing what happens at the beginning. you fix a given time and you look at the different trajectory, what is the probability to have n photons at that time, n minus 1, and so on. And you see that I use color codes, different colors to represent different photon numbers. You see 0, the evolution of 0 is quite clear. 0 will end up with a probability 1, because in the end, the field will have decayed. 1 photon is a red curve. At the beginning, the probability to have 1 photon increases and then decreases to 0. The probability to have 2 photons increases and then decreases to 0. And you can understand that quite easily because I show you here what happens. We start with a Poisson distribution. You see at the beginning, at a short time, it is what happens here. You see here that the highest probability is the blue one, which corresponds to 2 or 3 photons. And the probability to have 0 photon is much smaller. So this Poisson distribution corresponds to the cut here. If you wait more time, you see that, of course, the field will decay. So the probability to have 1 photon, which is a red curve, will increase. And at some point, the probability to have 1 photon will become larger than the probability to have 2 photons. And if I wait still more, I get a cut, which is at a longer time. And now this is the probability to have 0 photon, which is the largest one. But you see what happens is that the Poisson law is just translating back to vacuum, and it remains a Poisson law. The coherent state decays, keeping the same statistical shape until you are back to vacuum. And from this data, you can also reconstruct the average energy, and you find that the average energy decays exponentially. That is, if you take all the trajectories and take the average energy, you erase the quantumness, you erase the quantum jumps, and it is what you see if you have a very large photon numbers. You just don't see the quantum jumps which occur too fast to be seen, and you just see the average evolution. So on this kind of, with this kind of experiment, you can understand the connection between the quantum and the classical aspects. Now I will, in the last part of the talk, I will shift to another problem. For what I have studied here is how do you measure the observable, which is the photon number. Now, in this last part of the talk, I will measure another observable, which is a projector on a given photon number. You know that a projector is an observable which has the eigenvalue 1 if you are in the state on which you are projecting, and the eigenvalue 0 if you are in all the other states. So you can also define this kind of quantity, and I will show you that this quantity, which takes the value 0 and 1, you need only 1 atom to measure it. So how do you, what is the question? The question is, does the cavity, I suppose I have put again a coherent state in the cavity and ask the question, does the cavity contain n0 photon or not? For example, does the cavity contain 4 photons or not? So this amounts to measuring the projector on n naught, which has the eigenvalue 1 if n naught, if you have 0 n naught photon and 0 otherwise. And how can you do it with a single atom? And the answer is that you perform high resolution spectroscopy of atoms going through the cavity, and in order to distinguish the light shift corresponding to n naught photon. So I show you it here. And for that, I need a third level, a reference level. So now my energy levels are 50 and 51, and I have a cavity which is slightly off resonant with this transition. So it induces light shifts on this transition. And I have here the level 52, which is not shifted because it's completely off resonant with the cavity field. But 52 is a reference level, which will help me to measure the shift produced on the 51 state. So the cavity photons shift the level 51, but not the level 52. And what is the shift? The transition between 52 and 51 is the value it would have in free space. This is the atomic frequency in free space. And this is a shift produced by the fact that level 51 is shifted. And you see if the shift is upward, it will decrease the frequency of 52 to 51. You have a minus sign. And this shift is proportional to n naught plus 1. So you see that you have now a frequency for the 52 to 51 transition, which depends linearly on the photon number. And I present the spectrum here. Here you have the unperturbed frequency, which is the one you have in free space. Here, this is a frequency with 0 photon in the cavity. This is a Lang shift, omega square of 4 delta. This is the shift that you find if you have 1 photon in the cavity. This is with 2 photons in the cavity. This is with 3 photons in the cavity. So you have to decide where you are on this diagram. And what you do is that you shine on the atom a microwave whose frequency coincides with one of these peaks. So it means that, for example, if you choose this, make this choice, you will be able to go from 50 to 51 only if you have 2 photons in the cavity. Because if you have 1 photon or 3 photons, you are out of resonance. So you prepare the atom in 52 and you shine a pulse of light, which is resonant with one of these lines. But of course, it is difficult because this pulse will have a width, which is inversely proportional to the time during which you irradiate. And if the atoms go fast, it will be too wide. It's why we could not do this experiment with a horizontal beam. You had to do it with slow atoms, which take a lot of time to cross the cavity and to explore this shift. And so we use an atomic fountain, which we developed much after the experiment I described to you before. So what you need, it requires high resolution, hence long interrogation times. You need to have omega squared T over 4 delta larger than 1. So you need a long interaction time, several hundred microseconds. And for that, we use the setup that I mentioned already last week, which is an atomic fountain. You see now that we have turned, the cavity now has a mirror like that. And the atoms are prepared, you have atoms in a motte here, which is produced by lasers. And then you push the atoms up. So you create a fountain, the atoms are going across the cavity very slowly. But of course, you cannot push Rydberg atoms. In fact, what we push are ground state atoms. And so you have to get circular Rydberg atoms when they enter into the cavity. So we use these electrodes to apply a rotating radiofrequency field, which prepares the atom in the circular Rydberg state while they are in the cavity. So it's a rather complex experiment. And then you get slow circular states, and you can do this experiment with them. So you have this, and the first thing you do, which is quite obvious, you prepare a coherent state, and then you scan your microwave. And what you see is you see here. You see now that you resolve the light shift for the different photon numbers. So you see now that indeed, just by doing this experiment, you reconstruct the Poisson law, because each of these peaks is proportional to the probability to have each photon number in the initial coherent state. And you see here, in this case, the maximum is about 2 photons, and you have a distribution from 0 to 7 photons, like that. So you can now measure the light shifts corresponding to different photon numbers. We show that on the next slide here. You see that as a function of the photon number, the shift, what you expect according to the theory I described, to have a straight line. But in fact, you see it's not exactly a straight line. You have a curvature which is due to higher order perturbation theory. I assume I computed the light shift only to lowest order, but in fact you have corrections. But of course, when you analyze the result, you can take into account this. The red curve is a theoretical curve taking into account the higher orders. So this is first experiment, but now let's come back to the experiment to filter, in which you want to filter a given photon number. So what we do here is to set the frequency of the microwave in order to be in resonance with the light shift corresponding to n0 photons. So I've tried to show you here what happens. If you have n0 photon in the cavity, you are exactly resonant between 52C n0 and 51C n0. But if you have 1 or photon more or less, you see immediately that you are a little bit off. So in fact, in this case, you will select only the situation where you have 4 photons, let's say 4 photons in the cavity. And if the atom goes to 51, it means that you have the photon numbers that you had selected. So how do you see that? If atom is detected in 51C, it means that n-naught photons are selected in the cavity. To prove that, it's very simple. In the first part of the experiment, you apply a microwave pulse which selects a given photon number. Then on the same atom, which is still in the cavity, suddenly you put the cavity in resonance, and then this atom starts to do Rabi oscillation. And the frequency of this Rabi oscillation depends upon the photon number. And then in the end, you go out of resonance again in order to detect as a function of the delay. So you see, it's an experiment which has 3 stages. First stage, you select a given photon number. Second stage, you let the system oscillate according to the right frequency, Rabi frequency, and then you detect, and you do that by changing the Rabi oscillation time in order to reconstruct the Rabi oscillation. And this is what we observe here. So you see here the sequence. This is a function of time. This is the first sequence. You apply a microwave, which is when the cavity is shifted by about 100 kilohertz. So you get a light shift, which produces a Fock state, let's say 4 photons, 2 photons. Then suddenly you put the cavity in resonance, and during this time, you look at the Rabi oscillation, and in the end, you measure the probability to be E or EG. Then you change this delay, and you reconstruct the Rabi oscillation. So again, what you do is first a microwave filter, which selects the photon number, then a Rabi oscillation between 51 and 50, which should be proportional to square root of n-naught plus 1. So the signal is whether you are proportional to square root of n-naught plus 1 or not. And this is the result here. You see, if you select 0 photon, when you look at the Rabi oscillation, you see the black curve here, which oscillate at frequency omega naught. Now you do the same experiment by shifting your microwave in order to hit the light shift corresponding to 1 photon. And if you do that, you get the red curve, which oscillates faster because it's oscillated at the rate omega naught square root of 2. But you see that you have just 1 frequency in each of this curve, which shows that you have prepared Fock state. If it were not Fock state, you would have a kind of fuzzy Rabi oscillation. Same thing if you go now to 2 photon, which is a green curve, you get omega naught square root of 3. And if you go to the blue curve here, omega naught square root of 4, which is just 2 omega naught, this is what you get if you have selected n equals 3. And we can go up to n equals 4. This is the curve that you get if you have selected n equals 4. So you see this experiment shows you that with a single atom, you select a given photon number, and you use this atom to prove that you had selected this photon number by looking at the Rabi oscillation in this photon number. I also show you this here. You see this curve oscillates twice as fast as the first one. If you have 3 photons, the Rabi oscillation goes at the rate twice as 0 photon. You see indeed that 1 oscillation here corresponds to 2 oscillations here, and 2 oscillations here correspond to 4 oscillations here. It shows that you only have the square root of n variation of the Rabi oscillation. And to conclude that, you see that you can measure not only observable like the photon number, but you can also measure projectors on given photon numbers by using this technique. And again, these are things which are useful in quantum information science when you want to select some quantum state and to measure projectors on quantum state. This is something which is useful in quantum information procedures. So I will say a few words in conclusion of this lecture. I have described resonant and non-resonant interaction processes between atoms and photons in the strong coupling regime. In the case of resonant coupling, we have seen how to entangle atoms via either successive coupling with a cavity field containing 0 or 1 photon, and how to realize a quantum gate with a photon as a control on the atom, the target bit. In fact, I did not discuss experiment in which you can go to larger photon number. If you have 3 atoms, you can prepare 3 atoms in entangled state called GHZ state, Greenberger-Horn-Seidinger states, which are also state useful for quantum information. In the non-resonant case, which I think is the most interesting situation we studied, we exploit photon number dependent light shifts to count photons in the cavity without destroying them. So it's a quantum non-devolution detection to observe field quantum jumps and to filter photon number states out of coherent states. Now, what I will do in the last lecture next week is the kind of symmetrical situation. In this lecture, I studied what the field is doing on the atoms. And the atoms are the measuring device for the field. In the last lecture, I will do the opposite. I will look at what the atoms are doing on the field. And in this case, the field will be used as a measuring device for the atom. And what I will show you is that it's possible, if you have a coherent state, to split it into 2 components and to have a superposition of 2 coherent states with a relatively large photon number. And this superposition of coherent states are called in the jargon of quantum optics and quantum information theories, are called Schrödinger cat states, because they lose their coherence in a process which is very interesting as a way to understand the boundary between the quantum and the classical world. So last lecture will be devoted to Schrödinger cat state decoherence. And then in the last part of the talk, I will try to generalize what is being done in cavity QED to what is called circuit QED. In circuit QED, it's the same kind of situation, but the qubits are no longer atoms, they're artificial atoms, structures, superconducting junctions, which have quantized energy levels and which behaves like atoms, with the advantage that the coupling being stronger all happens at a faster rate. Here you see that the time scale are tenths, hundreds of microseconds. In the case of circuit QED, the time constants are more like nanoseconds. So you can have larger number of operations. These are systems also which you can organize on a chip. So it looks more like something which could lead to applications. And circuit QED is one of the most active fields in quantum information for trying to build a quantum computer, for instance. So I will discuss also that at the end of the last lecture. So we will convene again next Thursday for the last lecture. Thank you very much. Today it's a bit shorter.